Now, another thing that's important about the system to know is that the I/O module or the fabric extender itself does not do local switching on the fabric interconnect. So this means that every time that you send a packet that is going between two different blades, the traffic has to physically leave the I/O module, go up to the fabric interconnect. Fabric interconnect is going to layer 2 switch the frame, okay, assuming we're in the same subnet, the same VLAN. It's going to layer 2 switch the frame, and then the traffic is going to be switched back down through the fabric ports, or excuse me, through the server ports from the FI to the I/O module, and then I/O module to the blade. So if we think about that logical diagram previously, so let's say that we're trying to get traffic from blade number 1 over to blade number 3. Okay, so we have two different virtual machines that want to move IP traffic between each other. Okay, so let's say we're pinging between the two of them. It means that the traffic has to pin from the blade up to the I/O module. The I/O module is then pinned to the fabric interconnect. The fabric interconnect is then going to look at the MAC address table, or essentially the CAM table, same as we would have on a regular layer 2 switch, makes the decision. The traffic is then switched back down to the I/O module. I/O module then pins it to the destination blade, and then we have the traffic flowing between the two of them. So from a design point of view, what this means is that the blade system is not the most efficient when you're doing east-west traffic flows between the servers. So if you're comparing physical rack mount servers that are going to like 9Ks or going to 5600s as your top of rack switch, if you have workloads that are very heavy for east-west traffic flows, you would be better running those on standalone or rack mount servers that are not using fabric extenders, as opposed to the blade chassis, because we have to physically send the traffic from the I/O module up to the FI, and then from the FI down to the from the FI back down to the blade chassis. Now, there's a question here: was this changed with the Generation 3 fabric extenders? So Gen 3 would be like the 2348. There have been some enhancements for this where it does allow you to do some local switching on the FEX. But in 99% of the cases, the traffic is going to have to go up to the parent switch before it comes back down. So in general, if you have like a web server that's calling a database, east-west flows within the data center, you would try to keep those on rack mount servers that are not going to a fabric extender, because we're going to hit that oversubscription potentially problem that's going to be from the I/O module up to the FI. But what we'll see is that from a configuration point of view, what we are most concerned about is what is going to be the physical path behind the scenes of how the traffic is leaving the virtual machine of the hypervisor, or maybe it's a bare metal machine, whatever. So whatever traffic is on the server is going to be leaving the network adapter, so leaving the VIC card. It's going to go up to the I/O module, up to the fabric interconnect, and then up to the northbound network. This decision is going to be pre-decided by the fabric interconnect in what we call the pinning decision of the virtual network interface card, or of the VNIC. Okay, the reason why is that the fabric interconnects don't run as regular normal Ethernet switches by default. They have a different behavior depending on whether we're moving traffic from the southbound network, so from the blade server itself, southbound going north, so out the VIC card to the IOM, north to the fabric interconnect, and north to the northbound switch. The forwarding decision is different when we're leaving the system versus when traffic is coming back into the system. So if we were to think about this from like a compass on a map, you have north, south, east, and west. North, south, east, and west. So southbound is coming from the server, and then we're leaving the chassis physically, so we're going from south to north. This is going to be based on the pinning decision, and then when we return the traffic flow going from northbound to southbound, that decision is going to be made based on the normal destination MAC address. Okay, the reason why is that the system is running what we call end host mode by default, or NIV. This is sometimes called EHM for end host mode, versus Ethernet switching mode. Okay, we'll see from an operational point of view, there's some design cases where end host mode is not going to work and you're required to run in switching mode, but they're very, very few and far between. In 99% of the cases, you're not going to run in switching mode. You're going to leave it as the default behavior, which is running as end host mode. So we're going to come back to this when we talk about disjoint layer 2 connectivity and what are some of the more advanced design problems we run into with the system. But the key is that with the default behavior, when you take the system out of the box, go through the initial dialog, and then go to boot the servers, the Fabric interconnects are running end host mode both for Ethernet connectivity and for storage connectivity, which changes its behavior from a LAN connectivity point of view different than a regular Ethernet switch. Okay, specifically, what's going to change is that the Fabric interconnect is only going to be learning about MAC addresses on the server ports that are going southbound to the blades. So we'll see from a verification point of view when we look at the show MAC address table on the FI, we will know about the MAC addresses associated with the virtual Ethernets down to the blades, but we're not going to know about the MAC addresses of whatever the northbound destinations are, like the default gateway of the servers, or potentially other machines, anybody else that's on the same VLAN essentially that's connected to the northbound switches. We'll see that the forwarding decision is going to be a little bit different. Okay, additionally, when we're running in end host mode, we're not running spanning tree. Okay, so we talked about on the northbound switches, this is going to be from the 5K's point of view, the trunk interfaces that are going southbound to the Fabric interconnects. So if we look back at our physical diagram here, this is talking about from 5K1 and 5K2, this is going to be Ethernet ports 9, 10, and 11. We're going to configure these as just regular trunk interfaces going south, but we have to make sure that we're configuring these as spanning tree edge trunk ports. And I'll show the reason why it has to do with the synchronization process and the fact that the Fabric interconnect is not running spanning tree. Okay, the other change about this is that we're going to have what's called a designated broadcast receiver port, or what's sometimes referred to as the G-pinned port. This is going to affect designs where we have disjoint layer 2, and I'll talk about that in more detail later, specifically what that means, but the end result is that if you design this wrong, you can start to drop traffic when you're going towards certain destinations. Okay, so we need to understand how the pinning is happening behind the scenes, how the designated broadcast receiver works, and then from a loop prevention point of view, there's 2 checks that the FI is going to go through that we call the reverse path forwarding, the RPF check, and then also the deja vu check. Okay, the RPF check basically says, look at the port where the traffic came in on. If this is not the interface that the NIC is pinned to northbound, the traffic is going to be dropped. Okay, the deja vu check is to make sure that traffic doesn't leave on Fabric A and then return on Fabric B. Like if I was to send a broadcast northbound, I send it up one link to the switch, and if the switch sends that broadcast back downstream, the FI is going to know that based on some sort of internal packet counter it's doing, and it's going to make sure that we're not looping the traffic back down to the blades. So you don't actually have to configure anything to get it to do this. It's by default, all of this is going to happen. But we do need to understand how to verify this, because if you run into a situation where you're trying to send IP packets to the server and you can't ping it, basically it's a traffic black hole, 99% of the time it's going to have to do with this issue of the dedicated broadcast receiver and how the RPF check is working for the traffic that is going from northbound to southbound.